In this lecture, let us discuss the analog filter design using Butterworth method. Okay, so as I said in the previous lecture, we have two popular methods. The first one is Butterworth and the second one is the Chebyshev filter. Okay, now the Butterworth filter simply takes, let's say, HA of S excuse me, magnitude squared is equal to 1 by 1 plus capital omega divided by omega c to the power 2n. Okay, so the nth order Butterworth filter has a magnitude squared function equal to 1 by 1 plus omega by omega c to the power 2n, and this is the magnitude squared function of nth order Butterworth filter. And you notice that at omega equal to omega c, the magnitude HA of j omega c, if we substitute omega equal to omega c in this expression, then it becomes magnitude squared becomes 1 divided by 1 plus omega c by omega c becomes 1 power 2n is nothing but 1, so this is 1 by 2. Okay, so and you notice that at omega equal to omega c, the magnitude HA of j omega becomes 1 over root 2, or magnitude squared becomes 1 by 2. That means wherever the magnitude squared is half is the frequency at which 3 dB attenuation occurs. If you convert this in terms of dB, then this is equal to 3 dB attenuation minus 3 dB. Okay, so the point is wherever the magnitude squared is half is the frequency at which how much 3 dB attenuation occurs. So this is called 3 dB frequency. Okay, therefore omega c is called 3 dB frequency or 3 dB bandwidth of the Butterworth filter. Okay, so if we take a low pass filter, let's say the filter is like this, and this is capital omega, and take this is 1 and this is minus 3 dB. That means this point is half of the maximum value. I'm sorry, half the magnitude is half, therefore this point is called omega c. Okay, so it's not half of the maximum value, it is the half the point. See, the maximum value is 1 and you take half, and this one is not magnitude, it is the magnitude squared. In case if you take magnitude, then this 1 by 2 becomes 1 over root 2. Okay, so this is the point at which the magnitude is 1 over root 2. Okay, so that is called 3 dB frequency, and the maximum value is normalized to 1. Okay, now you also notice that if you let me properly plot it. If you plot the magnitude HA of j omega magnitude, I am not going to plot magnitude squared, but I am going to plot only magnitude. Okay, versus omega, the magnitude square goes down monotonically. Okay, so if you plot the ideal low pass filter, the ideal low pass filter looks like this. Let me draw in with a different color. So let's say this is my ideal low pass filter. Okay, so if you plot HA of j omega, magnitude versus omega, then this is ideal low pass filter. Okay, then the DC value is 1. DC value means the frequency is 1. Okay, and the value at omega c will be equal to 1 by root 2. So you take this point as 1 by root 2. So this is a free point at which the frequency the corresponding frequency is called omega c. Okay, therefore if we plot for various values of n, we will get plots like this. Let me plot one by one. Maybe it looks like this. Then the next plot, if you increase the n value, then it goes like this, and then take n is equal to 3 like this. Okay, so let's say this is n is equal to 1, and this black one is n equal to 2, and this red one is n equal to 3. Okay, therefore if we plot for various values of n, we will get plots like this. Okay, where capital N is increasing in this direction. Okay, so it is increasing this direction towards the down. So as you increase the order of the filter, all of them have same originating point. See, all the plots are originating in this point, same originating point. Okay, what is the originating point? The originating point occurs at omega equal to 0. And what is the value, corresponding value? 1. Okay, we are calling the pass band as the 3 dB frequency. So therefore 0 to omega c is called pass band frequency. And the beauty is everybody is meeting at this point. So at omega equal to omega c. See, all the curves start at omega equal to 0, and all the curves meet at omega equal to omega c. So that's an important point we should remember. Okay, at omega equal to omega c, the value is 1 by root 2. All of them have the same originating point. That originating point, and the originating point is omega equal to 0, and the value is 1, and all of them meet at omega equal to omega c in this point, and the value is 1 over root 2. And if these two condition occurs, then obviously there will be some error, right? Because this is my ideal, the top one is ideal, this one, but my curve goes like this with a different value. Therefore there is no slight deviation from the ideal value, and that is called error. Therefore error is defined as, I put this symbol for definition. Okay, so you should read it as defined as, put a triangle symbol on top of equal symbol, then that indicates defined as. What is the maximum value? 1, and minus your curve takes HA of j omega for different values of n. You take the magnitude difference, then this is called error, and this error decreases as you increase the n. Right? If you take let me choose some other color. Yeah, look at here, this red curve indicates, this red curve indicates n equal to 3, and if you plot for n equal to 4, again it slightly goes like this, n equal to 4. Therefore if you increase the order, the error value comes down. What about this color? This curve is nothing but n is equal to 1. When I say n is equal to 1, this is my error. Okay, this much error will be there. So if you increase the order, the error goes down, right? So the error decreases as the order increases. Okay, the error we mean the error in the pass band as well as the error in the stop band. Okay, you see the red curve has a highest cutoff slope. And one more point I would like to say is slope at the cutoff frequency. And as I said, this omega c is called cutoff frequency. And if you look at the slope, okay, for n equal to 1, this is the slope, it goes like this. For n equal to 2, the slope slightly increases. For n equal to 3, the slope is little higher. Therefore, if the order increases, the slope also increases at the omega c. Okay, it has higher cutoff, and therefore its omega s, the edge of the stop band, starts much earlier. Okay, so the edge of the stop band starts little earlier for higher order filter. So what you do is you determine the order capital N required for meeting the given specifications. Okay, if omega sub c is known, then that's all, okay, that you have to determine. If omega c is known, then all you have to do is to find the order. From this you find the order capital N that is required to satisfy the given specifications. Okay, so omega c is known, determine the order of the filter capital N. Okay, you should not over satisfy the specs by choosing a higher order. For example, let's say if n is equal to 4, don't take n is equal to 5 or n equal to 6 like that. Okay, because you should choose only the minimum possible order, right? Because if you make a mass manufacture, as most of the industries do, every increase in order requires a few dollars more, and therefore if you make 1 million of them, 1 million filters, Butterworth filters, the company has to incur a lot of loss. Okay, so the company has to incur a lot of loss. The company is usually stick to the minimum possible thing. Okay, the industries usually stick to the minimum possible. How much less can I spend to be able to earn how much more? So that is the company's general motto. Okay, spend less amount of money and earn more amount of money. Okay, and then from this curve you also notice that, maybe I'll draw one more time. This is the ideal low pass filter. Let's say this point is 1 over root 2, and the curve goes like this, and the next one is for n equal to 2, it goes like this. For n equal to 3, it goes like this. Now the curve is monotonic. Okay, that means it doesn't have maxima or minima. Okay, so you notice that the monotonicity of HA of j omega. Okay, so that means I can write the magnitude HA of j omega, magnitude squared, is equal to 1 divided by 1 plus omega by omega c to the power 2n. And then if we take this square root to the right hand side, then it becomes 1 divided by 1 square root of 1 plus omega by omega c to the power 2n. Okay, now I can rewrite this as 1 divided by 1 plus omega by omega c to the power 2n whole to the plus half. If you bring it to the numerator, then it becomes 1 plus omega by omega c to the power 2n whole power minus 1 by 2. And then if we expand this by using binomial expansion, then it is going to be 1 minus 1 by 2 omega by omega c to the power 2n plus higher order powers. Okay, higher order powers of omega c by omega c to the power 2n, right? And you see that if I differentiate the magnitude HA of j omega, if you differentiate the magnitude with respect to omega and put omega equal to 0. What will you get? Differentiate dHa of j omega magnitude with respect to d omega, then this is going to be 1 becomes 0, and then minus 1 by 2 2n times omega by omega c to the power 2n minus 1 plus some higher order terms. And then if you substitute omega equal to 0, then this will become 0. Okay, so if you differentiate, differentiation of 1 becomes 0, differentiation of 1 is 0, so you will get this 0. So if you put omega equal to 0, obviously this will be 0. So the next differential coefficient should also be equal to 0, and this will continue up to the ith differential coefficient, okay, where I goes from 1 to up to how many differentiation? Because I have the power is 2n, okay, so how many differentiation will vanish? 2n minus 1 differentiation will vanish, okay. So therefore 2n minus 1 differential coefficients will vanish. For example, if you differentiate x squared, the first differential coefficient is twice x. The second you differentiate one more time, then it will be 2. So the power is 2. So up to first order it becomes 0. If you substitute x equal to 0, then it will be 0. The second order exists. Similarly, here I have 2nth order, okay. Therefore 1 first order, second order, third order up to 2n minus 1th order will give to 0 if you substitute omega equal to 0, but only the last differential coefficient will survive, okay. That means what? If you differentiate and substitute omega equal to 0 and the function gives 0, so what is the meaning of that? Before that, let me write down this mathematics. So d differentiation of HA of j omega 2n minus 1 differentiation of 2n minus 1th order divided by d omega 2n minus 1 n, or instead of writing like this, let me write down in another way. D power I, d omega power I evaluate at omega equal to 0. This is 0 for I is equal to 1 2 up to 2n minus 1, okay. But the last coefficient d to the 2n magnitude of HA of j omega divided by d omega to the 2n, if you evaluate at omega equal to 0, then this is not equal to 0. Therefore you cannot think of any other function which will have twice n minus 1 differentiations vanishing at omega equal to 0. If one differential coefficient vanishes for a function at a particular point, then what do you say? We say the function is flat at that point, okay. Therefore I have 2n minus 1 coefficients will vanish at omega equal to 0. So that means my function is flat at omega equal to 0, okay. So it is either a maximum or a minimum, okay. So if I say this is flat, or I can put like this, so this is flat at this particular point, okay. So we say that the function is flat at this particular point, okay. It doesn't have maxima or minima. Therefore the Butterworth function HA of j omega is equal to 1 plus omega by omega c to the power 2n whole power minus 1 by 2, and let me call this is function equation 1, and this function, the Butterworth function, has a large number of derivatives and this derivative is vanishing at omega equal to 0, and therefore this type of function is called maximally flat function. Okay, so maximally flat at omega equal to 0. The order of flatness cannot be more than twice n minus 1. Okay, so that's all about the introduction of Butterworth filter. Now let us discuss the asymptotic behavior of the Butterworth filter. Okay, so the next question is that of the asymptotic behavior of the Butterworth function. Okay, and we know the function originates at omega equal to 0, and it meets, all function meets at this point where the magnitude is 1 over root 2. Okay, now the question is, how does it behave when omega goes to infinity? This is omega. Now my function goes like this, Now at infinity, let's say here omega equal to infinity. How does it behave at infinity? Let's see. Okay, as omega goes to infinity, the magnitude tends to, let us see where it goes. HA of j omega magnitude is 1 divided by square root of 1 plus omega by omega c to the power 2n. Okay, now if omega is large, right? See, omega tends to infinity means what? Omega is very, very large. Therefore, in that case, this 1 is negligible. Therefore, this becomes omega by omega c to the power 2n whole to the 1 by 2. So, this I can write omega by omega c to the power n. So, this is going to be omega by omega c to the power minus n. So, this is the asymptotic behavior of the Butterworth filter when n goes to infinity. Okay, so if you bring it to the numerator, you will get omega by omega c to the power minus n. Now we want to express this HA of j omega magnitude in decibels. Okay, therefore if you take log of this is HA of j omega magnitude when omega goes to infinity. Okay, therefore as omega goes to infinity, then the magnitude in dB is, this is magnitude, right? Therefore let me write the magnitude in dB, 20 log of magnitude of HA of j omega. Okay, log 10 h of j omega magnitude is equal to 20 log to the base 10 omega by omega c to the minus n. Therefore, this I can write it as minus 20 times n log 10 omega by omega c. That's it. Now, what do you understand from this? As the frequency goes to infinity and this guy goes to, the magnitude goes to minus 20n log to the base 10 omega by omega c. In other words, as omega increases by a factor of 10, the characteristic goes down by 20n. Okay, in case if you take omega is equal to 10 times of omega c, then what will happen? This is going to be 1. It's going to be 1, right? That means minus 20 times log to the base 10, 10 omega c by omega c will get cancelled. Log to the base 10 is 1, so it is minus 20n. This minus indicates it is going down. Okay, so therefore the characteristic goes down by 20n. And what is 20n? This 20n is expressed in decibels, and therefore the asymptotic slope is equal to minus 20n decibels per decade. Okay, so decade, and the same thing I can write as minus 6n dB per octave. Okay, and decibel is written small d and capital B. Why capital B? Because B stands for a proper name, and you must respect the name. So not small b, it's a capital B. Okay, so now omega increasing or decreasing by a factor of 10 means a decade. Okay, decade means what? Either you increase the frequency by 10 or increase the frequency by 10 or decrease the frequency by a factor of 10. Therefore, minus 20 times n dB per decade is approximately equal to minus 6n dB per octave. Actually, per octave it should have been 6.0206 dB per octave, but I can write approximately minus 6n dB. But for engineering purposes, we take it as a round figure 6n. So I said approximately equal to, but they are used interchangeably. It doesn't make much difference. Okay, this 6n and 6.0206 won't make much difference. Okay, octave is doubling or halving the frequency. Okay, suppose if omega is equal to 2 times omega c, or omega is equal to 0.5 times of your omega c, then the attenuation or magnitude changes by 6n dB. Okay, so this makes it clear that if you know the asymptotic slope, if you are required to design a Butterworth filter with 18 dB per octave, that is a given specification, okay, then you know that you require a third order filter. Okay, if the specification says we need 18 dB per octave, okay, so that means 18 by 18 is equal to 6n and n is equal to 3. You can find out. But this is not what the specification. Okay, so this is not the way to specify a Butterworth filter. So how will we specify the Butterworth filter? As I said, specifications will always be in the form of passband attenuation, stop band attenuation, then passband frequency and stop band frequency. Okay, so this is how in practice a required filter is specified. Okay, anyway, we will come back to this a little later. But before that, let us say if you know capital H A of j omega magnitude squared as 1 plus omega by omega c to the power 2n, then this right hand side is not adequate for designing the filter. Okay, with this I cannot design a filter. Okay, and this information is not enough for designing the filter. Then what else should I need? Okay, for designing the filter we require the transfer function HA of S in the S plane. As I said in the previous lecture, we need transfer function in the S plane. Okay, so this function is inadequate, so I cannot design the filter with this guy. Okay, so to design a filter I need the magnitude function in the S domain. Once you design the S domain, then you move back to Z domain using frequency transformation. Therefore we require the transfer function, And mathematics, there is a procedure, okay, and there is a process, and by using that process, the process is called analytic continuation. Therefore the process of analytic continuation says that HA of S times HA of minus S should be equal to 1 divided by, look at the function, this is magnitude square, and this must be equal to this one, 1 divided by 1 plus omega by omega c to the power 2n. Okay, you just replace omega by s by j. Okay, so in the above expression, then it becomes 1 plus s by j omega c to the power 2n. Okay, now bring this 2 to the s, then it becomes 1 plus minus s square by omega c squared whole to the power n. Okay, so s squared by omega c squared to the n, I can write like this. So in the left hand side I have HA of s times HA of minus s. It is obvious that okay, let me call this is equation A and this is equation B. Okay, it is obvious that I can go from equation B to equation A by putting s equal to j omega. In this, if I substitute s equal to j omega, then I can go back to equation A. The result is okay, right? But from equation A to equation B is possible only if the function is analytic. That is, we are looking for an HA of s. This function, we are looking for an HA of s which has finite number of singularities, and the function is finite number of singularity means what? The function is differentiable in the total S plane except at the singularities. That is the definition of an analytic function. Okay, so analytic function means what? It should have a finite number of singularities, and the function is differentiable in the total S plane or in the entire domain except at the singularities. Singularity is a point where the pole is located. So that's a definition of analytic function. So recall this definition from your mathematics course. Therefore, here HA of S satisfies the conditions of analyticity, and therefore what we require now is to find all the factors of this guy. Find out all the factors. Therefore, there are two demanding transfer functions. What are those two demanding transfer functions? One is HA of S and another one is HA of minus S. Okay, so if you multiply HA of S and HA minus A of S, then it becomes H of S magnitude squared. Okay, so this we got through the analyticity from HA of j omega magnitude squared. Therefore, we must find all the factors of this guy. All the factors of this guy we need to find out and assign. Let's say there are n number of factors you find out. Out of this n number of factors, half of them is assigned to HA of S and remaining half of them is assigned to HA of minus S. So n by 2 factors to HA of minus S and n by 2 factors to HA of S. Okay, so the factors that we assigned to HA of S must be such that their zeros are in the left half of the S plane. Okay, so this is my S plane. So when you assign the factors, then their zeros are in the left half of the S plane. Okay, it should not fall on the right side. Why? Because the filter will be unstable. Okay, so in the z plane they were inside the unit circle. If we take z plane, if you recall, for stable systems the pole must lie within the unit circle. Okay, in the s plane they must lie in the left half of the s plane. Okay, they must be in the left half for h of s to become a stable transfer function. Okay, stable transfer function leads to stable filter, that's all. Okay, it leads to stable filter. So we always wanted to design a stable filter, and therefore we must find all the roots and then make assignments. Okay, so I think let me stop at this point, and from here continue in the next lecture. Okay, thank you. So in the next lecture we will find out the poles of the Butterworth filter and try to see where these poles are going to sit on the S plane. Thank you.